All right, hello, welcome to my talk. My name is Simone Gasparinetti. I'm associate professor at Chalmers University of Technology in Sweden. It's great to give an invited talk here. And this will be a forward-looking talk as signaled by the presence of the word towards in the title. We would like to take the superconducting circuit architecture, which many of us are familiar with, and use it in a slightly different way, more in the way that is used in linear optics quantum computing. And one intermediate goal that you can set yourself when you do this is a proof of quantum speedup, which we would like to do in a verifiable way using a circuit QED platform. So today I will explain a little bit this idea, why we believe that this architecture could have an edge in performing these type of experiments, and also our preliminary steps experimentally to realize the building blocks that we need to achieve this goal. Let me also introduce my lab, the 22Q lab. We are an experimental group. We work with circuit QED. We have three main research lines. We work with quantum computing with bosonic codes, which is the topic of today's talk. We also work with proof of principle demonstrators in quantum thermodynamics. And as many of us in the field, we also develop quantum enabling technologies like amplifiers, switches, and filters. We also spun out a company called Sweden Quantum, who specializes in infrared blocking filters, and you can find them at the booth if you're interested. You can also look at our website to see what research we do. Let me also acknowledge all the contributors for this work. On the left-hand side, you have past and present members of my group who contributed to our CV computing project. And on the right-hand side, you have some theory collaborators from the neighboring divisions and some external collaborators as well. This research is mostly funded by the Wallenberg Center for Quantum Technology, which is a 12-year Swedish center to develop quantum technologies, and also by the European Innovation Council via a consortium project. It's called VeryQ. So as a final disclaimer before I begin, this is really work in progress. I very much appreciate your feedback. If you have some thoughts, think this is unreasonable or is a good idea, just meet me after the session. I'll be happy to talk to you. So to motivate this, I would like to sort of look at what quantum computing field is today. And much of the recent effort, which is fascinating, can be cast into two main categories, probably. On the one hand, we all would like to build a universal quantum computer. And we know this is extremely hard. At the same time, the problem is that we will be ultimately able to run some useful algorithms on it. For example, we know Shor's algorithm beats any classical equivalent, and we may believe there are more algorithms that are useful that you can run on a quantum computer, computational chemistry, but also other things. We also know we need more qubits, better qubits, and most of us would agree that we would probably, or most probably, require quantum error correction to do so. And this motivates much of the effort that we're seeing in these days, in these sessions. At the same time, there have been also attempts to make proofs of quantum computational advantage, which you can also call quantum speedup or quantum primacy, in which you're not necessarily trying to solve a useful problem, but one in which a classical computer has a hard time dealing with. And these are, so far, we have mostly looked at sampling problems. So with qubits, you can do random circuit sampling, and with continuous variable, most often in optical platforms, you can look at boson sampling and the variation of it, which is Gaussian boson sampling. These are some of the most important references, but that's not an exhaustive list, of course. So when you play this game, you would like to compare the performance of your quantum computer to the best classical algorithm run on the best classical supercomputer. And as the experts know, there are some catches in doing this. For example, it's true that it's very difficult for a classical computer to sample from an ideal distribution, but it's much easier to sample from a noisy distribution. And so if your system, if your quantum computer is noisy, the advantage is kind of eaten up. So now there is this race in which, on the one hand, you try to make your quantum computer less noisy, and on the other hand, you can try to make a better classical algorithm to beat the quantum computer. So it's, in a sense, an open race. And another aspect that you can find maybe theoretically disturbing is whether you can really verify that your quantum computer possesses the type of advantage you want, because the quantum computer does a difficult task, and you would like a verifier that has less computational power to still be able to tell whether the quantum resources are in there for the quantum computer to perform the task. So if we look at, so this concludes my overview of these two categories. And if we look at continuous variable quantum computer, which is of interest for this talk, but this is actually a very generic scheme of what most of quantum computing takes place. There is 3 key steps. There is a provision of some input states. There is some coupling network that entangles all these modes. And finally, there is a detection stage at which these modes are measured. Now, it is well known in quantum information that using now the language of quantum optics, if all these 3 steps are Gaussian or linear, this architecture is classically simulatable in a very efficient way. So if I input Gaussian state, I have only linear operations such as beam splitters and phase shifters, and then I have heterodyne detection at the end, there is nothing interesting to be done here. And so we have to break this Gaussianity at some point. And one way you can do it, for example, in Gaussian boson sampling, is by having photodetectors at the end instead of linear detectors. So what is our suggestion? Our suggestion is that we do what it has been done so far, mostly on photonic systems, on superconducting circuits. So the design you see at the right, it's a real design for a quantum circuit, but you can take it, for the sake of this discussion, as a sketch containing the main building blocks we're talking about. It's a planar superconducting circuit. It contains cavities and qubits. And our idea how to go about, how does that work? How to go about this architecture is that we would prepare non-classical states in these cavities over here, and then we're going to perform linear operation by beam splitting between these different modes by driving a central coupling element. And finally, we will perform measurements on these bosonic modes assisted by ancillary qubits that we have placed here along with the readout resonators. So this is an example for only 4 modes. What do we think we gained by this? If we look back at our cartoon of linear optics quantum computing, what we have is that we can prepare now, and I will show it in a few slides, but we have also seen it earlier in this session. We can prepare a very complex state deterministically using microwaves, for example, GKP states or CAT states, or generally highly non-Gaussian states with a high Fock number. And then we know how to do a linear beam splitter in circuit QD. But then the final requirement, which I find quite interesting, is that for many of these protocols, it is interesting to have different types of detections. And I think this need came up also in a previous talk of this session. Sometimes we want to look at CV quantum computing in the context of optics, and there is lots of things in optics that would require not photodetection, but Hom heterodyne. And we know that this is difficult in microwave modes. So this requires special attention. It's a problem that we like, and we have spent some time trying to solve. And I will come back to this later. So suppose we can do all this in circuit QD. What are the advantages if you compare it to the optics? So here we have a large Hilbert space for a single mode and the ability to prepare the states deterministically with high fidelity. Then if we can really toggle between these detection mechanisms in situ, meaning that with the very same sample, the same detector, we can do photodetector or we can do Hom heterodyne, we open the door for integrated verification protocols, such as this one that was suggested by our theory collaborators, in which you can use heterodyne detection to verify the performance of the quantum computer, and then you can switch to homodyne or photodetection to solve a sampling problem which is hard classically. And furthermore, I mean, we think we can do these operations with high fidelity and high efficiency, probably 90% above already the state of the art, and probably pushing it even further. So altogether, we think that this will put us in a competitive position, because if you compare to optics, in optics you have very many more modes, for example, in the order of a couple hundred. Well, these early demonstrations, they will be limited only by a few modes. But we are performing better in these other metrics. And we think that already with 6 modes, and maybe Fock state up to 10 or 15, we could be in the position with this low noise level to solve a sampling problem which is classically difficult. And this is a ballpark estimate, but this is where we stand so far. So what do we require on the hardware to realize this? State preparation needs to be very good. The beam splitters, they need to be good. Then we need to be able to toggle between these different detection modes. And of course, we need to scale, right? It's not enough to have 1 cavity or 2. Ideally, we would like to have some 10s. Realistically, we think we can couple up to 6 to a single coupler. There are also two shorter talks on these topics. One was given by Kunal earlier this morning in this room. And to scale these planar circuits, we have developed a quantum circuit optimizer that makes it very efficient to target some parameters. We will also release it as an open source later this week. But there is a talk by Lucas later this week. And I suggest you attend it if you're interested in scaling up quantum circuits to multiple modes. So in the remainder of this talk, I would like mostly to talk about these 2 things, state preparation and detection, which are 2 of these key primitives in this architecture. So when it comes to state preparation, generally, I mean, you can only prepare coherent state in a harmonic oscillator if you don't have access to nonlinearity. So a bit of a paradox of this architecture is that we want the systems to be very linear, but at the same time, we need a nonlinear controller to actuate them. And we have heard about this trade-off also earlier today. So 2 known pathways to achieve nonlinearity is to use a qubit as a quantum controller on the state of the cavity, or also to directly embed some nonlinear element which nonlinearity can be activated. Like, for example, we know elements like the snail or the ATS. They can be operated at the point of low static nonlinearity, but they can still be driven to create interesting states. So use the qubit as a quantum controller. This is a line of work that exists now for many years, more than 10. And this architecture is now very many familiar, in which there is a transmon qubit here in a 3D cavity dispersively coupled to a storage cavity. And this, in the dispersive regime, the frequency of the qubit depends on the Fock number of the cavity to first approximation in a linear way. So the qubit gets a different frequency dependent on the Fock state of the cavity. And this opens the possibility to address the qubit dynamics selectively on any Fock state. This has been used to implement one possible strategy to prepare states in cavities, which is based on the selective number-dependent arbitrary phase gates, and which I will now review very briefly. So this is a gate which, starting from the qubit in the ground state and the cavity in an arbitrary state, is able to stitch a deterministic phase to each and every coefficient of every Fock state in the cavity, while leaving the qubit again in the ground state. The way this works is precisely as I described. You want to drive the qubit selectively on the Fock state. And now in this little cartoon, for every different Fock state, the qubit gets a different block sphere, and you can have the qubit draw closed circles in this sphere. Depending on this solid angle, you will pick up a geometric phase, and this phase will be stitched to the given Fock state, because the dynamic of the qubit always goes back to the ground state. So this was my very brief explanation of a snap gate in a few seconds. We have specialized in implementing these snap gates and make them fast. And one reason we do it is that combined to displacement, if you combine the snap gate with the displacement, which is the most trivial operation to be performed on a cavity state, they provide universal control. So you can, in principle, prepare any state, starting from the vacuum. We have, this is one possibility. If you want to target a certain state, you can decompose the preparation gate into alternating displacement and snaps. And you can try to optimize this sequence so that it targets the interesting state. And This we did essentially with a two-step optimization approach. First of all, we found the best gate sequence to prepare a given state. I'm skipping some of the technical details now. But what is interesting is that we can control the phases of up to 17 Fock states at the same time, which we were quite pleased about. And then once we have the right sequence, we want to find the pulses to implement each of these gates. And this is where we use optimal control. And optimal control allows us to break some of the boundaries you have if you don't use it and approach the gate speed, which is quite close to the speed limit. Not exactly the speed limit, but we get much faster gates if you use optimal control. This is an example of the states that we can generate with this combination of snap and displacement. Interestingly, we can target very different families of states with this method. We can prepare Fock state, we can prepare a binomial state, a small cat state, even a GKP state, and a cubic phase state. And the fidelities of these are in the range of 90–95%, and they're obtained with very short gate sequences of just a couple snaps and displacements. More recently, we got also interested in this complementary approach in which we don't use a qubit directly, but we embed a nonlinear element inside the cavity. And in the first demonstration we did of this concept, we use a snail. So the snail stands for superconducting nonlinear asymmetric inductive element. It's a loop with several Josephson junctions, as shown in here. It can be operated at a carefree point, and then we can use parametric drives, both using the charge and flux degree of freedom, to induce several types of nonlinearities. Actually, if you expand the snail potential, what you find is nonlinearities at all orders, which can be activated dynamically. So if you take a lambda over 4 resonator and terminate it by the snail using a charge and flux drive, you get access to all sorts of different driving schemes. I mean, up to squeezing, we're in the domain of Gaussian interactions. And then the first non-Gaussian interaction is the third order, which gives tri-squeezing. One thing that we find interesting is that these nonlinearities can be activated very fast. I will show it in a moment. This is the first sample we measured, reported in this work. And this is a typical tuning scheme. This is the frequency of the mode as a function of the flux. And the plot below represents the third and fourth order nonlinearities. So the point with the star is the point where the self-care vanishes, but there is still a latent third order nonlinearity which can be activated by drive. These are some examples of what we can do when we activate this nonlinearity starting from the vacuum state. So you see, in only 20 nanoseconds, by applying a flux pulse, we can obtain a sizable squeezing of the cavity state. And if we drive a third order interaction, we can do tri-squeezing, also in only 60 nanoseconds, generating these states. And you see this little blue contour, this Wigner negative part of the Wigner function. It's a sign of non-classicality, which we obtained because we have gone beyond the realm of Gaussian operations. One thing that we do a little step forward is that we have combined different types of drive to generate a cubic phase gate. And then we have combined the squeezing with the cubic phase gate to generate this state, which is famous in quantum optics because it promotes Gaussian operations to a universal set if you have that state by gate teleportation. It's called the cubic phase state. And this is probably the best realization I know of this state, which is very difficult to prepare. And this is obtained in only 60 nanoseconds. So much for state preparation. I offered you, let's say, two options: to have a dispersively coupled qubit to do something like fast snap gates, or to have an embedded nonlinear element and drive it this way. And in either case, you get very non-classical states that are very promising to beam split to do the boson sampling. And now, in the remainder of the time, I would like to speak a little bit about the detection. So, of course, we have been doing qubit-assisted detection of a bosonic mode since a long time. Essentially, our general strategy to know something about the state of the cavity is that we map some cavity information onto the qubit, typically by an entangling operation, and then we read out the state of the qubit. With this strategy, in principle, we can ask any binary question to the cavity and get the answer with a quantum non-demolition measurement. Of course, some questions are more easy in the sense that they are natively implementable. Questions like, is a cavity in a Fock state, in a given Fock state, or is it in any of some Fock states? These are simple questions to answer because we can use Fock-selected qubit pulses. And these are very interesting because we know already that we can do photo detection, and we can also know that we can do photon number resolved photo detection, which is even more powerful. We also can tell the parity of the state, and we can tell the parity of the state after displacement, which is what we typically use to do direct Wigner tomography. And then if you have a generic question which is more difficult, you can still implement a decoding unitary, for example, using optimal control, and you can literally ask the cavity any question you like. On the other hand, there is some questions here that cannot be addressed by using the qubit once. And one such question is, what if I want to implement a single-shot homodyne or heterodyne measurement on the cavity? The cavity is a continuous variable system, and this measurement has a continuous range of outputs. So a single-shot measurement of the qubit will not tell you the single-shot homodyne of the cavity. Still, we have come up with a way to do it, which is what we call the qubit-dyne protocol. It's a protocol in which we use the qubit very many times, not just once. It works like this. We have exchange interaction between the cavity and the qubit, and we transfer a little bit of the cavity state onto the qubit. And then we measure it in a basis we can choose. Then we reset the qubit, effectively recycling it. We make it interact with the cavity again, and then we measure. So within what we call a single shot of the cavity, we may end up measuring the qubit tens of times. In our latest experiment, 60 times, getting a little bit of information at every step. And then what is interesting is that the choice of the measurement basis dictates which measurement type. If we just measure the qubit in the computational basis, we're making essentially a population measurement. So we're going to know something about how many photons there were in a cavity. So we're doing a photo detection. By contrast, if we measure on the x basis, we're performing homodyne detection. And if we are alternating the measurement basis between x and y, we are performing heterodyne detection. The way we get the single shot for these continuous variable measurements is by weighing the measurement outcomes with some weights corresponding to the fact that the cavity gets depleted as it repeatedly interacts with the qubit, which is always in the ground state. So there are some interaction weights, and this list of coefficients, this is a bit string of the single binary outcome of each qubit. Notice that is not relevant for this scheme, but the cavity is unconditionally depleted as a result of this, because every time the qubit starts in the ground state, it gets a bit of population and then is reset. So this is not a QND measurement. So, so we have done a preliminary experimental realization of this. We have used a 3D cavity, not the planar one. And of course, you need to implement the exchange interaction. There are different ways to do it. One way could be to do two-tone, to apply 2 microwave tone to induce a transition and effective exchange interaction using a 4-wave mixing process. And this was already done in previous work in a different context. But it can be done here, and it can be generalized to multiple excitation manifolds. So these are the very first measurements. They were taken at the end of last week, so we are really just lucky to have them today. I don't want to comment in much details. But what is interesting is that we're really targeting, this is an important point, what we want to target is single-shot detection. This is not it is not just a tomography technique. We are interested in the statistics of single-shot homodyne detection, which so far was impossible to achieve for a stationary mode with this efficiency. So these statistics that we collect, each count is really a sum over 60 measurements of the qubit, which has been interacted 60 times with the cavity and reset every time since. What we're pleased about is that these statistics has the right variance, 1 over square root of 2, which is already an indication that actually our measurement efficiency is really high. So this variance is not broadened. We measure the natural variance of the vacuum state, which looks very promising. It would make me think maybe our efficiency is 90% or above. And then what we have seen is that if we displace the state by alpha 0.2, okay, one of the quadrature doesn't move and the other one does. And these axes have been independently calibrated. There are some systematics we don't yet understand fully, but I would say that sort of 80–90% of the thing is there already, and now we need to fine-tune the details. So to be continued, yes. I'm jumping to my conclusions now. So we think this could be a good, interesting way to use our superconducting quantum hardware in a different way to try to get a quantum speedup proof similar to what is done in optics. And we have some disadvantages. We don't have many modes, but we can do very many things better, actually. Some of the building blocks we think are good enough already, like the state preparation, of course. And we are developing some of the others, for example, this homodyne detection. And also, of course, a linear beam splitter between 6 modes with all-to-all connectivity is not completely trivial. And we are working on it. And we will keep working on it. And in parallel, I think it's also interesting this work also opens some theoretical questions, such as what are the best initial states to start with to have computational advantages? Can we get hard proofs of hardness for this type of sampling? And we have theory collaborators thinking about this. So with that, I'll thank you and take some questions.
We'll have quite a bit of time for questions, so if you could just line up.
Thank you for the very nice talk. You say the homodyne detection is not QND due to the G preparation of the qubits. But did you try on playing on the initial state to make this homodyne detection QND, starting, for example, alternating G and E state of the qubits, so that you don't get energy away from the cavity?
I mean, you're suggesting that we try to correct for some of the systematics by flipping the qubit sometimes, or?
Yeah, or preparing the qubit in a different state each time to compensate from the loss of energy, for example.
But this won't work because then you're feeding something back to the cavity and
yes.
The state changes now. So
there isn't an optimal way to extract information. Like maybe you could optimize on the qubit initial state at each time, right?
I think that's an interesting question, but let's say intuitively, I wouldn't see how this works.
Yes.
I'd be a bit worried that the state of the cavity is compromised.
Okay.
But it's an interesting point. One could think about it. Mm-hmm.
Hi, thanks for the great talk. I was just curious, how long does it typically take for one of the qubit dyne measurements?
Oh, thank you. I skipped some of the detail. We try to squeeze everything in 1 microsecond. So exchange interaction, and then you need to rotate the computational basis to do the measurement and the reset. We do active reset, by the way.
Okay, and then follow-up is, what are your cavity lifetimes?
In this case, I think it's about 500 microseconds.
500 microseconds?
Yes.
Okay. That's just a single cavity, not coupled to anything other than that.
It's a 3D cavity in this architecture here.
Oh, right, yeah, you did. Okay.
But this already tells you actually, this already puts a bound on our measurement efficiency, right? Because the cavity has a parallel decay channel. And now if we can get it in, if we can get this measurement done in maybe 60 microseconds and the cavity lives, let's say 600, you can roughly calculate what the quantum efficiency of this measurement is.
Right, yeah.
Right.
And could I, for the, where you did the native cubic interaction and the Plato resonator, what were the lifetimes for those, or for that resonator?
That resonator, I think, T1 was probably tens of microseconds, but T2 suffers because it's a snail, there's flux noise, and you have a point with a slope. So there's probably just I think it was about 2 microseconds.
Okay, thank you very much.
No problem.
Thanks for a nice talk. So I have a question on the theory side of your quantum advantage. So what type of advantage is it? So is it similar to boson sampling, that the problem maps to like permanence of?
Yeah, it's sampling from a distribution, yes.
Okay, and it maps to permanence of.
I mean, the Gaussian, now you should ask a theorist. But
Okay. But there is a proof for hardness for this problem.
No, but our
Not yet.
theorists are trying to make one.
Okay, I see.
That's how it goes.
Okay.
Thanks for the talk. As someone who's not used to the language of continuous variable quantum computing, do you have a good intuition for, justifying calling the operation you do on the cavity like a single shot measurement? What would not a single shot measurement look like?
All right. I mean, let's say that you see here we're taking statistics of repeated measurements. So we did just not get the right average. We get the very same statistics that you get if you repeat a homodyne measurement with a quantum limited wave, for example, right? You get the right variance. That's what single shot would mean. That each of these, this would correspond. The statistics we obtain is the same statistics that you would get if you were doing perfect homodyne, right?
Okay.
If you were doing homodyne with finite efficiency, you would get a broader distribution.
Yeah. Okay. No, great. Thanks.
Mm-hmm.
Yeah, thank you very much for the nice talk. I was curious how you envision doing like multimode interactions to sort of scale this up to some potential universal computational model.
You mean like the beam splitter, or?
I suppose. Okay, yes. Yeah, well, sure, yes, exactly. Like a controlled beam splitter to be able to do that, like the circuit you draw with the 4 different resonators, how you envision doing this beam splitter control.
Yeah, you can do pairwise beam splitting potentially at the same time. It is also interesting that actually in our architecture we can also do nonlinear beam splitting, which is an additional resource, because in these 3 boxes, right, we have the possibility to make also the beam splitting operation nonlinear, which provides additional resource.
Okay, so in that circuit, like what element are you using to be able to control the beam splitter interaction?
Oh, it will be the first thing we're trying is either a snail or an ATS coupling element.
I see. Okay, yeah.
Either driven parametrically or directly.
Okay, yeah. Thank you very much.
No problem.
Hello. Thanks for the really nice talk. This might be a really dumb question, but what's the advantage of doing this cubidyne measurement rather than just directly coupling your cavity to the feed line and doing homodyne that way with, say, amplification?
Thank you. That's a great question, and I have not explained it. Of course, you have a series of loss channels if you do so, right? For example, you could think of letting your cavity mode decaying into a waveguide, hook it up to a phase-sensitive parametric amplifier,
Right.
and do it this way. I think the best efficiency people have gotten this way is about 0.4, 0.5.
I see. And here you can get higher than that?
Here we think we can get 0.9, 0.95.
I see. So it's for the higher efficiency.
Yes.
Right. Okay, thank you.
Which is critical. It will be absolutely critical once we move towards a quantum speed up.
I see. Okay, thank you so much.
Okay, we have time for maybe one question. Yeah, Jean.
Hi, Simone. Nice talk. So one issue with some of these continuous variable gates is that there are going to be a lot of extra parametric interactions that you probably don't want. Or it could be that you may want them. Do you understand, because they are all going to be non-classical. So do you understand sort of for this advantage quantum speed up thing, is there a trade-off between wanting a very pure beam splitter or a very pure cubic phase gate versus just doing something which is nonlinear?
It's a very good question. I think you may want to start from something you understand quite well. So typically we try to keep these spurious interactions at bay, as you know.
Right.
Right. But in principle, they are also a resource. So that's another maybe interesting question, what you could do with those. I imagine you would have to have them under control either way.
Okay.
But as I say, for example, nonlinear beam splitting is potentially interesting, is that I don't think many theorists have thought about it, because that's not how you would do it in optics.
Okay.
Okay. Maybe I'll sneak in one quick question. So you mentioned that some of the the initial states could be one of the ingredients that can offer the speed up, right, compared to optical implementations. Do you have some intuitions on what classes of initial states would be most favorable potentially, like
I mean-
large Fock states or cats or other sorts?
The theory is like GKP usually,
Okay.
from what I've heard. So I mean, GKP sounds promising, right?
Okay.
So that's
That's your hunch at the moment?
yes.
Okay. All right. Thank you very much.